let's go to some examples using truss examples. So let's go to some truss examples. Same problem. Just choose the same problem. And I want to find the deflection E. This question is asking, that was your question, what is the deflection of joint C caused by load P? Do I have a load in point C? I'm kind of stuck now because what wasn't the formula? Calculate the strain energy for the whole thing, and I will take the derivative with respect to P to get the deflection at point E, right? So if this is a deflection point E, that's how you did it, right? But this is asking me, what is the deflection point C? I don't have a load applied there. What do? I'll apply a fake load. And for listening, 20 points for you. I apply a fake load here, Q. Agreed? What can I do now? I can find the strain energy of the whole thing with that load P and that load Q applied. Agreed so far? And what will I do? I'll take the partial of U respect to Q first. And does the force Q exist? After you take all the derivatives respect to Q, once you're done taking those derivatives, set Q equal to 0 because it doesn't exist anyway. And that's the deflection at C. Isn't that cool? Oh, you're right. I should be using a different variable. Let's use rho. Somebody likes rho here, huh? And rho is not equal to density. Is deflection. I'm having fun. Okay, does that make sense to you? Do you follow the method? Well, we'll walk through an example here. Let's work through this example here. So first option, first method, sorry, not first method, but first approach, or sorry, not even that. The first step is to apply the load Q at that particular point C. Get all the forces in each of these cross sections as a function of P and Q, and set Q equals 0 after you take the derivative. So that's exactly what we did. We have find the reactions at point A and B. You do that, you get 3 force Q, 3 force Q. And you find that this reaction force is Q. Then we found the forces in each of these sections as a function of Q. You can see that we ignored the load P, by the way. You can see that we ignored it. But we didn't ignore it really, because guess what I did? If I solved this one earlier, right? I solved this one earlier. Remember I solved this earlier? Are you here? Hello? What can I do then? Superposition. I solved this one separately, take my time. And then here on the left side, I just ignored P and DQ and then added all the forces superposition wise. And that's exactly what was done. You can see here the force in each of the bars now have P and Q in them. And we use the results from previously that we had. Then I find the derivative of F respect to Q, which is part of the thing that we need to do. And I get these numbers, I know the lengths, I know the areas. You're pretty much done. And so your deflection now is a partial of F respect to Q, the energy respect to Q. Remember, energy equals what? F squared times L divided by 2EA, no? So the partial of all that gives you FLEA, the 2 cancels out, because F squared gives you 2F. 2 and 2 cancel out, you get F. And then partial of F respect to Q, we already calculated here in this column. Do you guys follow it? You don't have to do this chain rule, by the way. You don't have to do the chain rule at all. You can just do it, let me just show you, because I feel like some of you don't like this chain rule thing. I have the feeling, I could be wrong, but YC equals, let me do a couple of bars, you can see how this works. Partial of U respect to Q equals 0. What is the strain energy for bar set? Choose AD. Let's choose AD. What is the strain energy of that one? Of AD? 5P over 4 plus 5Q over 4 squared L 2EA partial of all this respect to Q. You agree? Plus, etc. I have to do it for each bar. So I'm just taking derivatives of this. That's all I'm doing. And once you set, and then once you take the derivative, you set it equal to 0, and you're done. And so I like this method better here because it's so simple, the steps. You find these derivatives, you put it in there. These calculations are easy too, and you're pretty much done. And now we set Q equals 0. You can see we did it, set equal Q is 0, and you're done. When you set it to 0, this Q goes away, and you're left with the deflection. Y equals this divided by E. Done. That's your deflection, which is really cool. We found a deflection at this point, although I didn't have a load applied. So step by step, step number 1, apply a fake load at the location where no load is applied. Step number 2, find the forces in each of the sections that you have. And that's going to give you forces as a function of that fake load you applied and the load P that's there already. Find the derivative of the total strain energy respect to the load that's fake. Set that equal to the deflection. But because that load is fake, after you take the derivatives, set Q equal to 0 after you make all the derivatives happen. And once you do, you get the deflection at the point that you're looking for. Isn't that cool? You can do the same thing. I can put a horizontal deflection that's fake also. You tell me what you mean, I'll do it. I'll make it happen for you. We can do that. Or you can make it happen in the exam.
Like say it was just like partial you expect to be set. That would use only for like
no, this, if I know the load P, I take the derivative of U respect to P, and then that's going to be equal to the deflection there. That's why I said earlier, don't substitute P equals 40 yet. Take the derivatives first with respect to P, and then you can do your substitutions. Yeah, but it's a linear system, so very likely P is not going to show up until the very end like that. You want to do another example just for fun? Just more examples. This came from a book I found. Height 4 meters, 3 meters, 3 meters. Load piece applied here. They're asking us to find the deflection point D at this location. So what is my steps? Find the energy here, 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 here. Add all the energies in terms of P. Find the derivative of U respect to P, and that gives me the deflection, period, right? Done. So what is the first step then in my process? Method of joints. So first do a free body diagram, and you find that this is P half and P half. Then do a cut here, do a cut there, do a cut there, do a cut there, do a cut there. And you can slowly make your way through to find. Exciting stuff. Okay, energy is exciting. All right, hold on. Okay, so we got this example here. And method of joints, I went through each joint and calculated the forces in each of these joints as a function of this load P. I'm not going to repeat something that was covered in statics. So I invite you to replicate these examples. And if you do, then you'll find the forces in each of these trusses here. And when you do, you find, then you take these derivatives, like I said before, So you take the derivative of each of the four bar forces with respect to P, and then use the formula I showed you earlier, and then that gives you the deflection here, very straightforward, 35 P over 4 AE. And towards the end of this lecture, I have a gift for you that I'll be announcing. Okay. Another example, I have these two bars here with a load applied P. Use Castigliano's theorem. But to your point, you're asking me how to deal with a situation where I have a horizontal load applied at point B. So you're asking me about a horizontal load applied B. This example is just like that. I apply a load P downwards, but I want to know how much you move right to the right or to the left. So what we did here, we applied a fake load Q to the right and redid the method of joints. We cut here, cut there, find the two forces very quickly, and then calculated the loads in each of these sections as a function of P and Q. P is known, Q is fake. So very straightforward. And then we took the derivatives like we showed before of the forces with respect to Q, the fake load. And then we calculated deflections in this manner. And you can see here we did it for you. And then set Q equals 0. And when you do, that's your deflection there. Very straightforward example. I have yet another example here where I apply a load here at point C. But I will not cover this example given that I provide you the solution here step by step. I'll be providing the slides for you to look at it. I'm going to pause every 5 seconds so it gets recorded, and that way you can pause the video and kind of replicate it. Is that fair? I'll be silent. Good enough? Get the loads in every member. Take these derivatives. You have the lengths. Do this calculation for energy. You know how to do this now? That's your deflection at the end. Over and over and over. That same formula. Same formula. Fair enough? So we're going to move now to beam examples.